This video is about epoxides, and we've already talked about it in terms of the Sn additions video, wherein the main point is that either of the reagents you use to make epoxides, MCPBA being the one you should definitely remember, attacks from the same side of the double bond and creates this little triangle sort of shaped ring, which is going to be highly strained, which turns out to make it incredibly useful for synthetic purposes. So the take-home message is, in the presence of metachloropurbenzoic acid, you can take a double bond and attach an oxygen to it in this sort of little triangle shape, and that proves to be incredibly useful for synthesis. Oxirane itself, which is to say just a triangle with an oxygen as one of the atoms, is incredibly useful, but more complex things are useful as well. And that's partially because you can open them under acidic conditions, for example, sulfuric acid in the presence of methanol, or under basic conditions like, say, using hydroxide and THF, followed by an acidic quench. And what makes this really valuable is you can do things like opening it with the anion of an alkyne or other organometallic reagents. And it's this last set of reagents that really matters for synthetic utility. Basically, we don't have very many ways in Organic 1 to make carbon-carbon bonds, and one of your best ones is going to be using alkynes and other organometallic reagents to open epoxides. That's one of your best ways of creating carbon-carbon bonds. And the main thing that we're doing here is we're taking advantage of the fact that this is highly strained, and therefore it's easy to pop open with all sorts of different basic reagents. And that's because even though O- tends to be a terrible leaving group, in this case it's not that bad because you're relieving a lot of strain. So O- can't usually leave, but it can leave in the case where you have an epoxide. And it's not really leaving, it's still attached to the molecule, but it's popping open, and that's what's relieving the strain. Alright, so the message here is that once made, these are incredibly useful. So how do you make them? Well, you take a double bond and you throw in MCPBA, and that does it, or you throw in trifluoroperoxyacetic acid, and that does it. So now let's talk about the mechanism of that. So all I've done so far is redraw the starting material in a perspective drawing, and I know that since the methyl was up and the epoxide part was down, that the reagent that's doing the reaction is coming from the bottom. Of course, this ends up being a racemic mixture because there's no particular reason why the attack should come from the bottom or the top, so you make both. But assuming that we are making this one as drawn, then the reagent that's coming in has to be coming from the bottom. The thing that matters here is the peroxycarboxylic acid part. So whether we're talking about metachloropurbenzoic acid, which has an aromatic ring as the R group, or trifluoroperoxyacetic acid, which has a CF3 there, the part that matters is the carboxylic acid and then this incredibly weak oxygen-oxygen bond that really drives the reactivity here. And again, from the Sn video as well as Magic videos, you know that this oxygen-oxygen bond is incredibly weak, which drives a lot of the chemistry, and it's similar to, say, bromine-bromine or chlorine-chlorine bonds, and again, that will be important for radical chemistry, which comes later. But in any event, what's going to drive the reactivity here is the fact that this oxygen-oxygen bond wants to break, and in particular wants to become a carbon-oxygen double bond because that's incredibly strong. And what's the driving force for that process to happen is the nearby double bond, which comes in and causes that bond to break. So the nearby double bond is providing the electrons that causes that to break. Again, it's going to make a carbon-oxygen double bond if it can, which causes this pair of electrons over here to come over and abstract the hydrogen, which would lead to the formation of a minus charge on that oxygen. But while this is happening, a bit of a plus charge is developing on that particular carbon. So these electrons will come by and then recombine, and that all happens at exactly the same time, which then leads directly to the formation of the observed product. And again, this is a highly organized transition state that involves all of these four arrows happening simultaneously. It all has to be organized just the right way, but this is relatively easy to do, and it generates this. And again, the driving force for this is the weak oxygen-oxygen bond and the fact that you're making a carbon-oxygen double bond simultaneously, which organizes all of this. So that's what makes this happen. Now, what happens next is a different set of outcomes depending on the conditions. So this is incredibly strained and will want to break, but it will break differently under acidic conditions and under basic conditions. And then, of course, organometallic reagents will come in and open it similar to the basic conditions, because just about every single organometallic reagent is one that has a minus charge on a carbon. So let's now contemplate the acidic chemistry. As always, the first step in any mechanism is to draw out both reagents in good Lewis structure forms, such such that we can use them. And furthermore, you should recognize that at the moment, the epoxide contains a pair of electrons, and if you have a strong acid nearby, it is likely to react with that pair of electrons. So you should contemplate protonating the epoxide. And this will be an equilibrium step, of course, but the first thing that's going to happen is we end up putting a plus charge on the epoxide itself, which should increase the chances that it will go ahead and react further. Now, of course, the key feature here is that even though the oxygen itself is plus, the reason why the oxygen is plus is because it now only has a single lone pair and also has 3 bonds to it. In other words, this material right here has an oxygen that is formally plus, but in practice, the plus isn't on the oxygen itself. The oxygen is instead more delta minus than you think in pulling electron density toward itself from the hydrogen or from the nearby carbons. And so really, what we have is a large amount of delta plus on the hydrogen itself, which is of course making sense because it could go back the way it came. Some base could combine and pull off that hydrogen and send us back that way. This set of arrows would then lead us back to where we began. On the other hand, we have 2 other places where there's a substantial amount of delta plus, and those will lead to a new potentially interesting product. So we should follow along what happens with them. And the thing I'll point out here is that you have a small amount of delta plus on this secondary carbon right there, and you have a much larger amount of delta plus on this tertiary carbon right there. Now, I've tried to indicate that by showing this bond as being bolder and this bond as being weaker, the idea being that the oxygen is small enough that it can't really cover both simultaneously, but you're going to need to weaken one of those bonds a little bit, and the bond that is better off weakened is the one that leads toward the tertiary because there's more stuff nearby to stabilize that delta plus. So the delta plus can be bigger at the tertiary position, and therefore it's going to need to be a little bit smaller on the secondary position, and so the oxygen is making more of a bond to the secondary and weakening the bond to the tertiary because this is the best possible outcome for what's going on there. One way we could get back out of this scenario is have the methanol come by and pull off the hydrogen, which would then take us back the way we came, but that is fundamentally uninteresting. So instead what we should have is the methanol come by and attack, and again what it's going to do is attack the area of greatest delta plus. So notice, because of where the oxygen is down below the ring, the methanol is going to have to come in from the top. As this bond is formed, as the carbon-oxygen bond is formed, it's going to cause this carbon-oxygen bond to break. But again, much like the bromoniums and the oxymercuration, we are attacking the area of greatest delta plus. In other words, this is going to be an Sn1 REGIochemistry. So you have to come in from the backside of the epoxide because the epoxide is blocking attack from the front, but it's going to attack the area of greatest delta plus, the more stable potential carbocation. Keep in mind, we don't have a carbocation, but this is carbocation-like, and this one is less so. So you're going to attack the area of greatest delta plus from the opposite side of where the oxygen is. In other words, the methanol is going to attack the tertiary side, opening the epoxide that way. The immediate result that forms is that the new methyl ether is on top because it came from the backside of the oxygen, which was down. The oxygen now opens and it is down, and then the methyl is just kind of along from the right, inverts, and the methyl ends up down. But you make this intermediate that is positively charged, and so then the final thing that happens is another molecule of methanol, your solvent, comes by to serve as a base and removes this proton, which then leads to the final observed product. In other words, what you isolate from the reaction is this one where the oxygens end up opposite each other and the opening happens at the more substituted carbocation. Not that you form a carbocation, but as if you had opened at the more substituted carbocation. So this is what happens under acidic conditions. Under basic conditions, what happens is that you simply do an Sn2 reaction under basic conditions. So you have a decent nucleophile, you have some polar aprotic solvent, and then separately in a second step, you do an acidic workup to isolate your final material. And so the idea here is simple. You are doing a Sn2 reaction, nothing more complicated than that, which means that you're going to attack the less substituted side, and you're simply going to open the epoxide from the far side. So again, nothing complicated about this operation. operation, it's just an Sn2 reaction. The only thing that's different here is ordinarily oxygen can't serve as a leaving group in an Sn2 reaction, but in this particular case, the reason why it happens is because the epoxide is strained. And so you are popping open that ring and relieving a bunch of strain, and that makes this vastly more likely to happen. That increases how good of a leaving group this oxygen is, because by opening, you can relieve the strain. So anyway, all we simply do is draw the hydroxide above here, and again, it's coming from the opposite side as the epoxide itself. So if the epoxide is down as drawn, then this will have to come in from the top, and again, what it will do is attack the less hindered side. This methyl is getting in the way. Unlike in the case where we add acid and we weaken this first and cause it to start to break already, here the epoxide is totally content. That is a normal sp3 carbon. So you attack the less hindered side, and that causes this to pop open on its own. The intermediate step that you make at first is going to be negatively charged, of course, and though that's not ideal, in the presence of a bunch of base, neither is it problematic. So we now have an O- sitting at this position, and what has now come in is the OH up at this position, and that's because you attack from the backside. So the new OH is up, the old bond that remains is the hashed oxygen, so the O- is down there, and this will sit there until you add in some H+ as part of the workup. And of course, I'm not specifying what acid is being used. Any acid you like will be a source of H+. You can't go to the shelf and grab a bottle of H+, but HCl, HBr, sulfuric acid, whatever. Even milder acids are happy to come in and take care of business. All you do is put that proton on, and there you are. Illustrating this a bit more precisely, as if we had used HCl, of course you abstract the H+ and put the electrons as a lone pair on the Cl. And so the upshot of having done this sequence of steps, first an Sn2 opening and then an acidic quench, is that now you make a very subtly different product, but one that I'm going to end up drawing right here. Note that the oxygen ends up opposite the other oxygen as well, but now you've opened at the secondary position and not at the tertiary position. And again, the key feature to recognize is that this is happening via an Sn2 process. So you are opening the less hindered side, and then you are quenching with acid, and this ends up being the product that you form once you have finished the quench. So the last piece that we need to talk about here is that you can do this kind of epoxide opening with organometallic reagents. At the moment, what I've drawn there is an alkyne, and specifically I drew acetylene deprotonated with sodium, but it doesn't have to be. It could be any alkyne. Our group could be anything you want, or it could be any other source of organometal type reagents, and we'll go into that a little bit more in a separate video, which organometallic reagents you can make, which ones you can use, and so on. But it doesn't really matter. In all cases, an organometal is going to behave the same way, as though it was carbon minus. So either the alkyne with an explicit minus on it, or an organometallic reagent of some variety. What they will do is open the epoxide under essentially Sn2-like conditions. That will then lead to a new R group at this position, whether we have the triple bonds or whatever other R group we're using. Again, it's just simply an Sn2 type reaction. And then you need to do some kind of acidic quench. Again, it's going to be H+. It doesn't really matter what the other thing is, but illustrating it with HCl, there you go. And so again, the specific product that we would make in the case where we open the epoxide with specifically acetylene would be to have the methyl be up, the OH due to the previous oxygen be down, and then of course the new group came in from the top. So here would be a wedge, and then you'd have a triple bond there if the alkyne were the thing doing the attacking. As illustrated with this particular alkyne, we would have an R group there. As illustrated with this particular material, we would end up having just simply an R group down at that bottom position. And again, the key feature here is to recognize that your epoxide can be opened by any manner of organometallic reagents, and those are Sn2-like processes that are opening at the less hindered position and with the stereochemistry you'd expect from an Sn2. So, big picture, you can make epoxide epoxides easily by using MCPBA, and then you can open them in a number of different ways, and some of those are more useful than others. The acidic epoxide opening will give rise to certain products, but the ones you really care about are the ones that are synthetically useful, and you can make carbon-carbon bonds by using an alkyne to open an epoxide, by using an alkyne to open specifically oxirane. You attach 2 carbons and an oxygen. You could use other organometallic reagents, and that will be the subject of an upcoming video. Learn how to use epoxides. You will use them in synthesis. It's one of the best ways we have for making carbon-carbon bonds.